Hi everybody. We're going to walk through a purely theoretical discussion here in Introductory Econometrics talking about the so-called Classical Linear Regression Model assumptions, also known as the gauss-markov assumptions, right? So we're presuming that we are comfortable now with the ordinary least squares model in terms of the mechanics of how estimation occurs, how that B0 hat, B1 hat, etc. coefficients are estimated. We've got an idea of measuring goodness of fit with the sum of squared residuals, the R squared. But now, before we can do anything further in terms of extracting interpretation out of those coefficients, we need to make some assumptions. So we're going to be laying down kind of the bedrock model of how we expect different components of that regression equation to behave, primarily the error term, that's going to allow us to kind of lay down the conditions under which it's going to be the optimal model. The OLS model is going to be the best choice for fitting a relationship to a scatter plot of points, essentially. So depending on what textbook you're following, these can be presented in a lot of different ways. So I'm going to be following kind of the convention of the Studenmund textbook in chapter 4. And so we'll be doing everything in kind of fairly basic notation. Everything is kind of in intuitive or summation mathematical notation rather than matrices. But let's go ahead and walk through this little discussion. So first off, when you're first kind of met with the idea of the ordinary least squares estimator, it's generally proposed that, yes, there are other ways of fitting a linear relationship to a sample of data points, but this is the best way to do it, choosing the intercept and slope that minimize the sum of squared residuals. Well, now we're kind of at the stage where we want to actually show that this is the best possible option. And this list of assumptions is going to be the conditions under which that is true. We still have the proof to do. So just, again, laying the groundwork. So again, in terms of vocabulary, the classical model, the CLRM, the gauss-markov model, the classical assumptions, that's what we're looking at here. Okay, so just to kind of go through the list here, and then we'll walk through them one by one fairly quickly, because the ones that are really going to come back and be important, guess what? There's a whole chapter devoted to each one of them later on down the line. But assumption number one, that the regression model is linear, correctly specified, and contains an additive error term. So that's, again, pretty much a purely mechanical assumption of how the regression model, how the data generation process is assumed to be constructed. Item number two, fairly intuitive, but there's a little bit more to it. The error term has a zero population mean. So the average error is 0. That makes sense. All explanatory variables, so our x variables, are uncorrelated with the error term. And again, on the face of it, this makes sense, right? If the error term is purely random, it shouldn't be correlated with anything, including the x variables. More to uncover there. Assumption number 4, observations of the error term are uncorrelated with one another, the so-called no serial correlation or no autocorrelation assumption. And again, on the face of it, seems pretty obvious. If my error term, if I'm an observation, is a random outcome, again, it shouldn't be correlated with anything, be it an x variable or your error term, a neighboring observation. Lots of reasons why we should be concerned about this, but just to introduce the topic. Assumption number 5, this is a good one, the so-called no heteroskedasticity assumption. So this is the first time you're running across that word. It's actually a word. So the assumption here is that the variability of the error terms are all the same. Every observation has the same variance about its 0 mean. So we'll dig into that one. Number 6, no explanatory variable, again, our x variables, is a perfect linear function of any other explanatory variable, the so-called no perfect multicollinearity assumption. good reasons why that's going to be important. And then lastly, one that we're just going to just briefly touch on, that's going to come back and be very important in a little while, is that the assumption that the error term is in fact a normally distributed random variable. So a very specific behavior assumed there. Okay, so let's take a look at these one by one. So assumption number one, kind of a lot packed into one assumption here. The regression model is linear, correctly specified, and has an additive error term. For the most part, this assumption just allows the mechanics of ordinary least squares estimation to take place. The mathematical operation of minimizing the sum of squared residuals is going to require a model that is linear in parameters and with an additive error term. So kind of looking at just a generic model here, y, so it's a multiple regression model as a function of x1, x2, dot, 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 through xk. This is what we are talking about, right? The coefficients, the b0, the b1, the b2, etc., through bk, enter into the equation in a linear form, right? So we can check that off. And the error term, rather than being, say, multiplied by some function of our x variables, is additive. We kind of tack it on to the end there. So when we think of a typical regression model, that's what it looks like, and it clearly meets our criteria. The big thing to keep in mind here is that when we talk about linearity, again, it applies to the coefficients, the b0, the b1, etc., not the x variables themselves. As we'll see in a couple chapters, we'll get a lot of mileage out of doing things like this, right? Looking at an x1 squared, looking at a quadratic function between x and y, but the coefficient is still linear, right? So as long as that holds, assumption number one will be met. Okay, what do we mean by that last portion, the correct specification? Really what that means is that somewhat magically, the model that we've gathered data for and are estimating matches the true unknown underlying data generation process, that we've included all the right variables and they appear in their right form. If we're supposed to square a variable, we square it. If we're supposed to log a variable, we've logged it. So we haven't missed any variables that are important, and we haven't misspecified them in terms of their functional form. So a lot to ask for right out of the gate that we're getting this exactly right. Okay. So just as an aside, well, what if we were violating these assumptions, right? So what would a model look like that was in fact non-linear in parameters? You don't have to think too far to see, in economic theory, where these nonlinear models are very common. So a Cobb-Douglas form production function or utility function or cost function, etc., would look something like this, where the parameters, the alpha and the beta, are in fact the exponents attached to the x variables. Here would be output as a function of our intercept, which would be representing our technological growth, labor to the power alpha, the labor share in our production function, capital to the power beta, and we would want to find the alpha hat and the beta hat. And what this assumption is saying is we couldn't directly do that with OLS, right? Because of the nonlinearity in the parameters. Our first order condition and formula for OLS approach that we've established isn't going to work. All right, so keep an eye out for that. Again, in a couple chapters, we'll see how we can solve this problem. Taking the natural log will linearize that function, but attacking it directly with OLS, assumption number one says, can't do it. Okay, so the OLS procedure essentially will break down in attempting to estimate those coefficients. Assumption number two, the zero mean of the error term. So we think about this in terms of the expectation of all the possible error values that could occur for each individual observation across repeated samples, right? That's why this gets a little bit tricky, because when you first see this, you'd say, well, okay, of course the errors are going to average out to zero, right? Because we're putting that line through the middle of the observation. So half will be positive, half will be negative. they'll average out to 0. That's not what this is saying, right? What this is saying is for each observation, all the possible outcomes that it could occur, the randomness is going to be centered on 0. So it's the dimension is across repeated sampling within each individual observation. Okay. And again, think about what we're capturing here. When we talk about that error term, it's in the data generation process, right? The variation in the y variable, the dependent variable, that is not explained by the model, right? Once we've extracted all of the explanatory power, we've included all the x variables that matter, everything that's left should just be purely random variation across repeated samples. And again, that's going to occur for every observation. So the picture would simply be this, right, where our error term for each observation, so call it u sub I, varies across samples, right? So if we're, think of an example, if we're trying to track daily consumption values, right? And you wake up in the morning and there is some predicted level of consumption, but today you spend a little bit more because you were, whatever, you were hungry at lunch, so you bought a little bit extra, so you had a positive error. You dial back the clock, you start that day again, and this time you end up having to skip lunch and do extra work, so you end up spending a little bit less. So it's just this random variability, right? Sample by sample in a hypothetical framework. So the center of that distribution is at 0. That is our assumption. Now, the reason why this is going to be important can be seen if we just tweak that little picture here, right? So we take that distribution, put it on its side, and attach it to each observation in a, stick with the example, in a little hypothetical consumption function, right? So this is our predicted level of consumption up and down that line for 3 observations, observation 1, 2, and 3. And then each sample that occurs is going to give us a random deviation above or below that prediction. So imagine we run through, again, that hypothetical day, right? And person 1 spends more than predicted. They have a positive error. Person 2, a little bit less. Person 3, a lot less. That is our sample, right? We put that through our regression formula, and we end up with a prediction line that looks like this. That is one sample estimate. Rewind the clock, right? And say, let's play that day out over again. And just by random chance this time, person 1 spends less than predicted. They have a negative error. Person 2 and person 3 have positive errors. We plug those observations into our formula, and we get a wholly different prediction function. Call it our sample 2. So this random variation that occurs across samples for each observation is going to generate what's really going to be important here, variability in our OLS estimation. Much more on that to come. But that's kind of the way you want to think about the 0 mean random error. Is each observation is going to play that part. Okay, that was getting good. So now assumption number 3, the covariance between every x variable and our error term should be 0. All explanatory variables uncorrelated with the error term. And again, this seems obvious, right? If we did everything right, if all of our x variables account for the explained variation in y, then everything else has to be random, and random variables are uncorrelated with everything. So it stands to reason it's going to be uncorrelated with x. The problem is, rarely do we get it exactly right. Okay, so the assumption is that we do. So if this is not true, if that covariance is not 0, well then our OLS estimates, our slope coefficients, our partial y, partial x, will be likely to attribute to the x variable in question some of the variation in y that actually comes from the error term, that should actually be attributed somewhere else. So this is going to be opening the door to what we'll call biased estimation. Okay, and again, much more on this later on, but just to kind of think through an example, if the error term and the x variable were positively correlated, then the estimated coefficient, the b1 hat, right, would be higher than it would otherwise. It will be biased upward. All right? The impact of that error term is being absorbed by the x variable, making it look more important than it should in determining that y variable. So we're going to get a systematic mistake, essentially, pivoting that regression line upward with respect to x. Okay? And really what we're doing is drawing the distinction very clearly here between exogenous factors and endogenous factors. The assumption that we're making, assumption number 3, can basically be rephrased in a succinct manner and just saying the assumption is that x will be an exogenous variable. It will be uncorrelated with the error term. It's fixed. It's non-random. It's determined outside the model. So whatever randomness is happening to the error term and the y variable, it's not touching the x variable. The exogeneity assumption. What we're concerned about is when that assumption is violated, the covariance is not 0, x now becomes a partially random variable within the model. It's an endogenous factor, whereas it shouldn't be. Okay, so a random shock to the error term affects y and x at the same time. We don't want that to happen. And again, the classical model assumption is that that's not happening. So just to, I said I'd only talk about this briefly, just dig one more layer down. Just kind of think about a regression model in flowchart form, right? A causal diagram, if you will, of what the model is supposed to look like, right? So we have y as a function of x and the error term, and x and the error term are uncorrelated. They're independent of one another, right? So this is what's supposed to happen, right? Variation in y comes partly from the error term, partly from x, and the b1 hat that we estimate entirely reflects the impact of x on y. Fantastic, right? So we can interpret that as partial y, partial x. We can tell our little story, and we are good to go. Here's the problem. What happens when x is now an endogenous regressor? We have violated assumption 3, and now the variation in y, coming from x and the error term still, but there are other relationships happening, right? A change in the error term can affect x, or the error term can affect x through y, right? So we get this kind of what we'll call a reverse causality scenario. Well, now this b1, right, we're not sure what this represents, right? Because now a random shock to the error term is going to be influencing y this way, and it's going to be influencing from y to x this way potentially, and we can no longer exactly interpret that b1 as reflecting the marginal effect of x on y. It's going to be a biased estimate. So again, much more on this as we move forward, but for now, the story is this is what we believe to be happening, right? In order for our classical model to hold, it's this simple story. Okay. One more. Just kind of an obvious scenario here. What we're really talking about is, when does correlation mean causation and when does it not? When have we left out a big important factor in the error term that's correlated with both x and y? So this came up in my Twitter feed a while ago from the New York Times health section, normally an interesting read. So let's just read it. So, want to live longer? Try going to the opera. Researchers in Britain have found that people who reported going to a museum or a concert even once a year lived longer than those who didn't. So the implication obviously is that there's a causal link, right? Engaging in these cultural activities, that's the x variable, is going to be positively influencing y, which is how long you live, right? Your longevity. Absolutely sounds great. So this is kind of the causal diagram from x to y. You go to the concert or go to the opera, you live longer. Well, obviously, there's lots of things going on that are not being controlled for here. Kind of the obvious thing that they're missing is wealth, right? So people that have more money are both more likely to go to the opera and have access to quality health care, so therefore they live longer. So playing the role here in our regression, that wealth variable, because it's not in the model, is a part of the error term that's clearly correlated with the x variable of opera, biasing the apparent causal effect of x on y, longevity. So again, the assumption of the classical model is we're not doing this, right? That we're controlling for everything, pulling it out of the error term that might be influencing that y variable. Phew, okay. Next assumption, number 4. Observations of the error term are uncorrelated with each other, the no serial correlation assumption. And again, on the face of it, no problem. Errors are random, so they're uncorrelated with each other. Not always so easy. So in slightly more technical notation here, we're assuming that the covariance between u sub I, one error term over here, observation I's error term, and some other error term, u sub s. So here's observation I, here's observation s. Those are going to be totally uncorrelated, right? So the assumption is that this is equal to 0. If this covariance or this correlation is not 0, well then in a sense the error terms are no longer truly random. An error term can be predicted by its neighboring values. And we would say that that regression, that model suffers from an autocorrelated error or a serially correlated error. So there's a whole chapter on this that we're going to get to later on. Most often this is going to be an issue in time series models, but not exclusively. But it's kind of easier to think about in those terms, where if there's, say, a random shock in the stock market, say today, we're still going to be reacting to that shock tomorrow, right? So u sub I is today, u sub s is tomorrow. They're going to be linked. Right? There's going to be unexplained variation that relates to each other, relate to one another over time. Okay. So putting it into time series notation, right? If the error term ut plus 1 is correlated with u sub t, then the error term is said to be serially correlated or autocorrelated, and thus violating our assumption for. So t plus 1 would just be tomorrow, t would be today. Okay. So when we get to chapter 9 of our Studenmund text, we're going to take a deep dive into this issue, but again, for now, we just kind of go on our merry way. We're in our little classical model bubble and assuming error terms are purely random, uncorrelated with one another. Same thing here with assumption number 5, the no heteroskedasticity assumption. Or the other way to say it, the other vocabulary word, we assume that the error term is homoskedastic. Same variability, right? Heteroskedasticity, different variability. Homoskedasticity, same variability. So it's the assumption that each error term has exactly the same variance about its mean. In other words, the dispersion of that distribution, picture that little bell curve distribution, is identical across all observations. Another way to think about it is we're just copying and pasting, right? The same distribution. My error term behaves the same. It has a 0 mean, the same probability of being well below or well above that 0 mean as every other error term. Okay. So if there is a change in that variability, if my error term observation is more variable than yours, well then that model is heteroskedastic. So it might look something like this, right, where we're thinking about variability as how widely dispersed observations are from that prediction line. This is kind of the classic picture of a heteroskedastic error, where at small values of some, what we'll call a scale factor z, variability is pretty small. As z increases, variability rises. So just kind of picture that bell shape, did not draw that very well, that bell curve distribution spread out well above, well below here, and here would be a low variance distribution, something like that. So kind of the classic example, and it fits the picture here, would be the variability of household consumption as a function of wealth, right? So if you have no money in the bank, you're not all of a sudden going to go buy a boat one month and have a huge level of consumption well above the prediction line, and you're not going to be way below the prediction line because you're already at kind of subsistence level. Whereas if you've got $100 million in the bank, well then, yeah, one month you might just buy a mansion, or you might just kind of stay home and not spend nearly as much as you normally do, but plenty of spending to live on. So just the possibilities of variability change with that scale factor. Again, a whole chapter on this coming up later on. For now, we just assume this is not happening, right? That variability is constant as we move up and down that prediction line, move up and down the sample. Assumption number 6, the no perfect multicollinearity assumption. So I know these vocabulary terms are coming at you fast. When we talk about autocorrelation or serial correlation, that is relationships amongst the error terms. When we talk about multicollinearity, put these in your flashcards, right? We're talking about correlation amongst independent variables, our x variables. So note we're saying not that x variables can't be related to one another, it's that they're not perfectly predictable based on another, right? So no single x variable can be perfectly predicted by a combination of other variables. So if we do have this problem of perfect collinearity, and it does happen, usually because we made some mistake as researchers, you might double count, right? You might include the same variable twice on accident, or one variable might be constructed as a perfect multiple of some other variable, or one has just been shifted up or down by some constant. When that happens, you'll know right away. We'll see examples of it when you're playing around running regression in Stata or R. You're going to get an error that simply says, oh, I couldn't calculate that coefficient because you've already done it, right? You're trying to use the same information to get two separate coefficients, and it's just not going to work, right? So examples, no reason why you would do this, but if you're trying to control for, say, an individual's weight and you've included both weight measured in pounds and in kilograms, well, that's a constant conversion. The variability in one exactly matches the variability in the other. You'll get this perfect multicollinearity error term. The much more common scenario is with the so-called dummy variable trap, right? Where you've included one too many binary dummy variables than are necessary to capture all of the possible outcomes. So if you're trying to control for gender, you only need one dummy variable. You've got the control group and the treatment group, say male versus female. You don't need to flip that around and have a second dummy variable with the same information. Again, the good news here is, unlike the other assumptions, here you know when you've made this mistake, right? The other times, OLS is generally going to work fine. You're not going to know on the face of it if you have an autocorrelated error or a heteroskedastic error or an endogenous regressor. Here you will know. Whew. Got to the last one. Assumption number 7, there's a reason why we're kind of skimming over this one, is it's an optional assumption that the error term is exactly normally distributed. We don't need that assumption to get the result that we're going to prove next, which is that the OLS model is the optimal predictor. Having this kind of known functional form for the error term is going to be necessary for hypothesis testing. So that's our next chapter after we do our proofs. So it is definitely going to come back to be very, very important. But it turns out for now, it's kind of a throw-in. It's optional, but it'll come back to be hugely important. And just think about why this is going to be important, right? The probability density function is going to be determined only by the mean and the variance, or the mean and the standard deviation, right? Mu and sigma. So as long as you know what those two parameters are, we'll be able to calculate the probability of seeing any specific value. And this starts from the error term, but the neat thing is it's going to build up, right? And if we can show that if the error term is normally distributed, well, then the y variable is going to be normally distributed, and the OLS estimate is going to be a normally distributed random variable. That's going to be crucial. Okay, so I know we went through this very quickly. Make sure you spend some time on it. In fact, my first assumption, this again comes from chapter 4 in the Studenmund textbook. If that's the book you're working from, read that chapter very carefully, right? Whatever chapter is laying out the classical model, make sure you've got the vocabulary, you've got the concepts down. So read it again. Yes, memorize the assumptions, write them down, make your flashcards, right? And for each one, kind of do a little bit of what we did, but more so. Just think about, well, under what circumstances would this assumption not hold? What would a model look like that wasn't, that didn't have that no autocorrelation or no heteroskedasticity result? Right? And again, we'll fill in a lot of those blanks a little bit later on. So what comes next? This little story that we've been telling, the behavior of the error term described in these assumptions, right, is going to have a huge impact on how the OLS estimator, the B1 hat estimation, will behave. And if those assumptions are true, then it's going to be a pretty straight line, easy result to get very useful causal implications out of an OLS regression. When one or more of those assumptions are violated, then we're going to have some more work to do. So in a sense, from here on out, our kind of discussion of introductory econometrics, it's all going to come back to this list, right? When are these assumptions true? When are they not? How can you tell the difference, and how do you fix it if there is a problem, right? So can't stress this enough. Make sure you're comfortable. Make sure you understand these assumptions. And again, the good news, we're going to be coming back to them and digging into them in more and more detail as we move along. But for now, there's our little walk through of the assumptions. Hope that was helpful. See you guys next time.